In the previous sessions, we discussed some concepts like transactions, verification of transactions, and the last subject was Merkle trees. Now, in this topic, we are going to talk about blocks and mining, okay? So, let's have a review on the transactions. As I said, every node in the network, all the it's a peer-to-peer network, okay? All the nodes into the network, you can consider Bitcoin or any other cryptocurrency. There is no difference. All cryptocurrencies have a network. All have a peer-to-peer network. Every node like this can create a transaction, say transaction number 1. Then this node multicast the transaction to other nodes. They verify the transaction, and then again these transactions will be propagated through the network, okay? Some nodes are called miners, okay? Miner. These miners get the transaction and put them inside a block. So miners create blocks, okay? As I said, this is a blockchain. Block 0, block 1, and each block has a description. For example, 0, 0, and also each block has its previous description, so it's like a linked list, okay? Now we have some transactions. Transaction 1, transaction 2, transaction n. Each node, these transactions are recently transactions, and they must be put inside a block, okay? They are kept in a data structure called mempool. This is a list of not confirmed transactions. Not confirmed transaction means the transactions that didn't put it inside the block yet, okay? So miners, each miner choose some of these transactions and create a block, put the transaction inside the block, and this is a way that a block is created. But there are some very, very important subjects about creating blocks. Why? Because if I'm the miner who is responsible of generating a block, I can do many things with the transactions. I can change them. I can create fake transactions. I can double spend my money. So it's very important that who can create a block and how. So in this lecture, we're going to talk about blocks, creating a block, which is called mining, and different methods to add a block inside the blockchain. Okay? Let me share these slides. Okay? How many transactions are allowed in one block? It depends. It depends to the cryptocurrency. For example, in Bitcoin, you can put, I'm not sure, but I think less than 1,000. The number of transactions is not important. In fact, the memory used is important. Okay? I'm not sure, but I think in Bitcoin, each block must be less than 1 megabyte. So 1 MB. Okay? In other cryptocurrencies, it may be different. So some transactions are smaller than some others. So it's not a fixed number of transactions, but the memory, the used memory for each block must be less than 1 megabyte in Bitcoin. Okay? So certainly there is a maximum amount of memory and maximum amount of transactions. No sound? Can you hear me? Hannah, I think it's okay because others can hear me. As you can see, they are asking questions. I'm trying to answer, and there is no problem. Okay, let's start. So, in this lecture, I'm trying to talk about blocks. Okay, what is a block? A block is a list of some transactions. A block is a unit of a blockchain, is the smallest unit of a blockchain. Each blockchain consists of some blocks, one like a linked list, one after another. Okay, and in this lecture, we are going to talk about blocks, mining, and the related subjects. Okay? There are some traits with creating blocks. Let's check some of them. In Bitcoin, as you know, there is no central authority. Okay? So how do we decide what blocks get created and what transactions get into it? For example, suppose that there are 1,000 transactions, which must be chosen to get inside the block. And who can decide about these transactions, about the block? As you know, everybody can join the network in all cryptocurrencies, okay? And also, everybody can validate transactions. In the previous lectures, we talked about transaction validation or transaction verification. If you can remember, we use digital signatures and verification of digital signatures to validate every transactions. Okay, in principle everybody can make a block and put it in the blockchain, but in principle. Now what can possibly go wrong with that? With what? If everybody can make a block and put it at the end of the blockchain, there are some problems, there are some threats. One of them is fake chain attack. What is fake chain attack? Suppose I join the network and I want to buy some bitcoins. Okay? Eve can make a fake blockchain in which she has evidently got the UTXOS. What does it mean? If everybody can create a block, so someone like Eve can cheat. Someone like Eve can create a fake blockchain and convince me that it's a real blockchain. So I give my transaction to Eve to put inside the block, got my money, and after that she disappears. So if I'm convinced, I can lose my money and never find Eve again. Okay. Another problem, double spending. I can make two blocks at the same time and put them at the end of the blockchain. So I can spend the same UTXO in both. Okay, this is double spending. So choosing a proper approach for creating blocks and putting the blocks at the end of blockchains is very important. Okay, so this is the second trait. The third, Sybil attack. Sybil means female prophet, but I don't know what's the relation between Sybil and the meaning. Okay, it's not important. What is a Sybil attack? Sybil attack. A malicious actor makes lots of nodes to take over the network. For example, suppose that the network has only 100 nodes. If I'm malicious, so I create 200 nodes and control the network and change every transaction and cheat, and by cheating I got the money from others and they lose their monies. Okay, now how to deal with these problems? Satoshi drew inspiration from a system called Hashcash, which inspired an idea called proof of work. So the solution is proof of work. Now let's talk about what is a proof of work. The first idea is about 1993, about emails. You know what is junk emails, you know what is spams. Okay, everybody knows what is a spam email. The first attempt to prevent spams was a solution that was proposed in 1993. If we compare the emails with the hard copy of mails, what's the difference? It's not possible that receiving many mails, hard mails, I mean, in fact, something like this, 241 letters in one day. It's not possible. Why? it means that in real or hard mails, there is nothing like spams. Why? Because it's costly. If you want to prepare a letter, you must pay some money for a stamp. I will send the slides, don't worry. You must pay the money of a stamp, then you must spend some time to putting the letter in an envelope, then going to the post office, and that's all. These stuffs needs cost. Okay, now what's the proposal? What's the solution? The solution is make it costly to send email. Not very costly and not money, but work. You want to make it easy enough to send one email, but hard to send a million emails. How? So you make mailers solve a puzzle to send an email, only a few seconds. Suppose that each email to be sent needs a few seconds. For sending just one email, 2 seconds, for example, it's okay. But if you want to send some spams, for example, a million email, it will be very, very long process. Okay? And this was the basis of an idea to use in cryptocurrencies, which is called proof of work. And at the first time, it was used in Hashcash in 1997. Okay? Proposed by Adam Back. And later on, this idea was used by Satoshi Nakamoto. And what is proof of work in Bitcoin? The idea is only the node can be allowed to place a block on the chain who solve a puzzle. So every node that wants to create a block and put it at the end of the blockchain must solve a puzzle. How you prove that you solve the puzzle? You prove that you solve the puzzle by giving everybody the solution. The puzzle is very hard to solve, but it's very easy to be verified. It's hard to solve, but it's easy to recognize the solution. Okay? Now, let's see, what's the Bitcoin puzzle? The puzzle is based on a hash function using SHA-256. Let's call this hash function H, okay? So H means this hash function. Suppose if is a string, S is a data, so H of S, in fact, is the hex version of the generated hash for the S. This is a string of hexadecimal characters. How long is it? As you know, the output of SHA-256 has 256 bits. So H of S is 256 bits long, okay? Each hexadecimal character has 4 bits. So the length of the output will be 64 characters. And we can consider this 64 characters long hexadecimal format as a number in the usual way. We can convert this 256 bits to a number, okay? Now we have a description of the most recent block, the last block in fact, in the chain. Suppose that this description, in fact, the description of the last block on the blockchain, suppose that it's big B, okay? And here is the puzzle. Find a number n such that h of b dot n is small. B dot n means concatenating n, this number, at the end of b, then calculating the hash of that must be a small number. N is called nonce. Nonce means a number which is used once. A number which is used once, okay? We all are familiar with base 10. Consider 4-digit numbers. 4-digit numbers are from 0 to 90. They are all less than 10,000. Yes? Now, which of these numbers start with a 0? Very easy. All the numbers from 0 to 999. They are all less than 1,000. So there are 1,000 numbers. There are 1,000 numbers which starts with a 0 between 4-digit numbers. Okay. Now, between these 4-digit numbers, which of these start with 2 zeros? The answer is 0 to 99. They are all less than 100. So there are 100 4-digit numbers that starts with 2 zeros. Okay? So if we are looking for a 4-digit number less than 100, we are looking for 2 leading zeros. And now let's back to hex numbers. It's not 56, it's 64. Okay, 64. Let me 64, and here 64, 64, 64, 64, 64. I think here must be 63. 63. Okay. Now consider hexadecimal numbers. 64 characters or numbers. They are all between 0 to 16 to the power 16 to the power 64 minus 1. Okay. Now, which of these start with 1 0? The answer is 0 to 16 to the power of 63 minus 1. Maybe you ask, this number, this 16 to the power of 64 comes from where? Okay, let me to show you the output of, just a second please. The output of SHA-256 is 256 bits, okay? Every hexadecimal number, this is hexadecimal numbers, 0, 1, 2, 3, A, B, C, D, E, F, okay? 16, in fact, 16 characters, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, okay? So, these characters needs, the number of these characters is 16 and needs, every character needs 4 bits. So in hexadecimal, we have 256 divided by 4, 64 characters. Each character has 16 choices from 0 to F. So 16 to the power of 64 minus 1 is all the numbers created with the length 64 hexadecimal. Okay? 1 place, the second, the third, and the last. The first, the second, the third, and the last, 64. Here I can choose from 0 to F. So here I have 16 selection, here 16, here 16. So all is 16 to the power of 64. Since the numbers starts from 0, we must minus this number by 1, okay? So all the numbers are from 0 to 16 to the power 64 minus 1, okay? Now, which of these start with 1, 0? If the first position here, if here is 0, so we have just 63 positions. So it's 16 to the power of 63 position. They are all less than 16 to the power of 63. Which of these starts with k zeros? The answer is 0 to 16 to the power of 64 minus k, okay? And now, again, the Bitcoin puzzle. We have a description of the most recent block put on the chain, called that B. Here is the puzzle in more detail. Given a target T, T is called the difficulty of the network. I will discuss it in the next lecture. So our network has a difficulty, say T, given a block description B, find the nouns that if N is concatenated to the end of B, then hash of Bn must be less than T. And this is the puzzle which must be solved by the miners, by the node that want to create a block. And this is a proof of work. Okay? Now, what does small mean? It means that the number starts with some zeros and how this helps, the puzzle takes a lot of resources to solve. You could not make a new blockchain. You could not make a lot of miners. You could not make 2 blocks at once. Okay? Let me show something in Python to better understand the concept of mining. In fact, I want to give you the Python code of a miner. Okay, it's very simple yet very interesting. Let me find the code mining. Okay. Here we go. Here we have again some libraries to be imported. As you can see, cryptography hazmat. Okay, there is something called difficulty. Can you see the screen? Can you see the screen here? Okay. This part is the list of libraries we need. In the previous codes also we have used them. Okay, there is a variable called difficulty and it's calculated by a formula by all the nodes. Okay, but here I don't want to talk about how to calculate difficulty. In the next lectures we will talk about difficulty, but consider difficulty shows how hard is the puzzle. If you consider difficulty 100, means that difficulty is too low. Okay, but considering bigger numbers means that difficulty is higher and the puzzle is more difficult to solve. Okay. The target. What is the target? As I said, the target is a number that the output of the hash must be less than the target. So the target is calculated using this formula, 2 to the power of 256 divided by difficulty. Now I have some data. This is big B. Okay, this is big B. It's not important. Consider it some information. I have defined a hasher here. In the previous lecture, I showed you how to hash different data using SHA-256. Okay. Now hasher update data. This is data. So I hash the data. Hasher. Now hasher is the hash of data. Here I have created a copy of this hash. So hasher2 is the copy of hasher1, and nouns, this is nouns. Okay, nouns starts from 0. Okay, that's right. Here, by this command, I convert this integer number to a byte value. Okay, so this command converts the nouns as an integer to byte data type. Okay, here I added these nouns to my hasher. Remember, this hasher is the hash of data, and now here I put these nouns at the end of the data and I generate the hash of my data. Using this command, hasher to finalize, I create the output of the hash, called it block ID. Here, by this command, I convert, as you know, the output of the hash function is a 64 characters long hexadecimal number. Using this command, I convert this hexadecimal to an integer. So I store it in a variable called block ID int. And now I check. While block ID int is greater than my target, I calculate another nouns. See here, nouns plus 1. The first value is 0, then 1, 2, 3, 4. Again, I convert the new nouns to byte. I put it this hash contains many information. In the next lecture I will show you the details, but just let's talk about the mining process. Okay, this hash contains many information. For example, transaction inside the block, for example, the timestamp of creating the block, and many other information. But yes, one of the information is the list of transactions. So I check the here I create the new nouns. I generate again the new block ID, and here again I continue this process while I found a number that is less than or equal to the target, and at the end I print it. Let's start from a very easy problem. Just difficulty is 10. If I run the program, this is my solution. This is the solution of the block. Okay, just 1 0 at the end. Okay, just 1 0 at the end. Let's change it some harder. Now the number of zeros is 2. 1000. Now 1 million. Let's check. It's time consuming, as you can see. I don't know how long, but let's wait for some seconds. Oh yes, 1 2 3 4 5 zeros. So when you increase the difficulty, the number of zeros will be increased, and the puzzle is harder. Please note, finding the solution is hard, by checking is very easy. For example, I say you, I want announce, let's announce, please give me announce that generates a hash with just 1 0. This is the solution. 7. Now 2 zeros. This is the solution. 478 and 1 million. As soon as a miner finds the description, finds the new hash, okay, this is the nouns and this is the solution. And now suppose that difficulty of a network is something like this. Find n such that the hash starts with 6 zeros. Okay, this is the puzzle. Finding it maybe is a hard task. By checking it is very easy, because when you say we all have the data, we all have this data, when you say this is the solution and this is the nouns, simply I can use these nouns, put in just like calculate the hash of this data, then I put the hash of these nouns, something like this. Okay, I concatenate the hash of the nouns to the hash of data, then simply I can check that this number is greater or less than target. If is less than the target, so the solution is right. So solving this the puzzle is very hard, but checking it is very easy. As soon as a miner solves the puzzle, submit the solution, the string and the nouns to the network. So other nodes check the solution, and if it's a right solution, accept it, so a new block is calculated. Now if I want to solve these 6 zeros, why number of 6 zeros? I think I must change the difficulty to something like this. Okay, I'm not sure what I think, and you can check that. The Python, okay, this is Python. Power usage moderate. Okay, you can see that the mining process uses many electricity, because it must calculate different hashes and it's time consuming. As you can see, for this difficulty, 10 million till now, it's a minute, I think, my computer couldn't solve the puzzle yet. Okay, and the current difficulty of the network is something like this: 21.4 trillion. Trillion means 12 zeros, okay? 12 zeros to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the current difficulty of the Bitcoin network. My computer is a Core i7 computer, okay? For just difficulty 10 million, it's 2 or 3 minutes that it tries to find the nouns, yet couldn't. And now suppose that for such a difficulty 21 trillion, okay, it's a very, very large number. How many times we need to find the nouns? And this is the proof of work, okay? So only nodes can create a block. Only nodes can put a new block at the end of the blockchain who can solve such a puzzle. Okay? As soon as a miner solves the puzzle, the miner sends the solution, sends the answer to all the nodes, and other nodes check that, and if it's okay, then they will accept and a new block will be added to the blockchain. Let me stop it, and maybe just 1 million, and I don't know, now 4 million. Start. What is it? Formula. No. Okay. You see, power usage. Anyway, it's not important. You can run it later. I will give you the program so you can run it on your computer, and you can you can solve different puzzles, but okay. Let's stop the program, and this is a simple version of a code which each miner run and tries to solve the puzzle in this matter, okay? Now let's continue. Let's talk more on the puzzle. Okay, this is the Bitcoin puzzle. We have a description of the most recent block put on the chain called B. B is some information. We have a target T, as I showed you in the code. We have T is calculated using the difficulty. Given a blob this description B, find the nouns that hash of B dot N is less than target. Okay. This is some calculations. As I said, we are searching to find hexadecimal outputs with some zeros, starting with some zeros. Okay. I talked about this. So we can convert the problem in a way that we need to find a hash output which starts with K0. K is determined with the difficulty. Okay. How difficult is the puzzle? Let's see. What's the probability that hash of B dot nouns begins with K0? Let's calculate the probability of finding this. The probability of starting with 10 is 1/16. Why? As I said, in each place, say for the first place of the output of the hash function. Okay, we can have 16 choices: 0, 1, 2, 3, 4, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Now we have 16 choices. If we want to choose only 0, so it's 1/16. So the probability for 10 is 1/16. Now the probability of having a string starting with K zeros is 1/16 to the power of K. So as you choose bigger K, as you increase the number of starting zeros, the problem is getting more difficult and more difficult, because the probability is the probability of finding such a number will be decreased. Okay, it's a very, very small number, this probability. As you saw, I hard code a variable for message and ran through nouns starting from 0, stopping as soon as I got the 1 with an output with 10, printing out the attempt. Here my attempt number 1, number 2, number 3, and in the 12th attempt I found a string with 0. This is the nouns. Okay, now finding an output with 2 zeros, it's need 467 attempts, as you saw in the codes. Yes. Now, how hard is the real problem? The difficulty is something like this: 23.58 trillion. As I said, it's a very, very big number. In fact, on average, we need to run 9 times 10 to the power of 22 attempts to mine a block. And It's a very, very big number. Just think about that. 10 to the power of 22. 1 million is 10 to the power of 6. Okay? Just 6 zeros. But what's called 10 to the power of 22? Million, milliard, trillion? I don't know. It's very, very big. And maybe running this solver on my computer maybe needs several months, even 1 year. Okay? So in reality, people use some special hardwares called ASICs, which has many GPUs to solve this puzzle. Okay? And this is proof of work. This is proof of work and solve many problems using this kind of proof of work. In fact, prevent many people to cheat, prevents many people to create fake blocks because they must spend many times. They must spend many electricity, and it's costly. Okay? Maybe you ask, using this kind of proof of work really prevents others to create fake blocks, prevent others to thief money of people. In many cases, yes, but there are some exceptions. You can search through the Google. I think in Ethereum, 2 times till now, someone using a very large electricity. I'm not sure, but I think the cost is something like $10 million. The cost of that electricity. In fact, they rent some CPUs from some clouds, okay, and paid $10 million for 6 hours. 6 hours. And in these 6 hours, they stole nearly $150 million. So they spent $10 million to buy electricity, in fact, to buy CPUs and GPUs from a cloud, and in 6 hours they could steal $150 million Ethereum. But today it's very hard because the network of Ethereum and the network of Bitcoin is very, very big, and it needs a very large amount of electricity to get the control of the network. In the next lectures, I will talk about these threats. I will talk about these attacks. But now let's concentrate on mining and adding blocks on the blockchain. So we need another lecture to finish the mining process, to finish the how block is created. What I must explain you what information are inside the block. As you know, each block contains some transactions. Okay. There are other information beside transactions. For example, there is a Merkle tree, there is a timestamp, and the description of the previous block, and some other information that I will explain in the next lecture. Yes, do you have any question, Ahmed? Okay, and that's it. Tomorrow I will send you the slides and the Python code. Please remember me if I forget. Yes, tomorrow in the morning I will send the slides and the code, so you can run the code, and I will give you an exercise. It's a very simple exercise. Just give me a table with two columns. The first column, a hash output of my program, and in the second column, the nouns. And tell me, with your computer, with your laptop, with your PC, what's the biggest number of zeros which you could find? Consider a time limit for this. For example, 1 hour. Say me, in 1 hour, the biggest number of zeros I could find by my computer was, for example, I don't know, 5 zeros, 6 zeros, and give me the nouns and the hash output, so I can simply check that it's okay or not. I can give you the transaction code because it's not mine, okay? And you don't need the transaction code. That's part of the Zim coin. Also, in the next week, as I said, we have an exam. Just the grade is just 2 marks from 20, 10%, okay? And from the beginning, 4 or 5 questions from the beginning and to the end of transaction verification before starting Merkle trees, okay? I want you all be familiar with the questions and be ready for the next month examinations. So in next week, say Tuesday, we will have an exam, 4 or 5 simple questions and very simple questions from all the topics that I discussed in the class. So see you in next lectures, and thank you all. Yes, exam on Tuesday at 7 p.m. okay? I will announce it into the group 1 or 2 days before, don't worry. If you have any question, please let me know. Otherwise, let's say you bye-bye.